Hello and welcome back for some more beam analysis. In this lecture, we are going to take what we previously looked at in terms of understanding internal forces and how the internal force diagrams work and the relationships between them, and now we're going to apply a very systematic approach to solving beams. This will allow us to solve any beam with any type of loading. So let's see how we do that. Before starting any analysis, we must define the sign conventions for internal forces. There are three internal actions in a beam: axial force, shear force, and bending moment. Axial force is taken as positive in tension and negative in compression. For bending, positive moment corresponds to sagging deformation, where the beam curves with the bottom fibers in tension and the top fibers in compression. It's essential that we remain consistent with these conventions throughout the analysis, as they determine the shape and sign of the internal force diagrams. We now outline the systematic procedure for analysing beams. First, we define the loading and support conditions on a clear, well-labelled sketch. Second, we determine the support reactions using equilibrium, as covered in previous lectures. Next, we use the method of sections by introducing cuts at points of interest along the beam. These cuts will allow us to write equilibrium equations and derive expressions for the internal forces. Once the expressions are obtained, we evaluate them at key locations and use the results to construct the axial force diagram, the shear force diagram, and the bending moment diagram. This structured approach ensures that the analysis is clear, consistent, and easy to follow. The type of support used in a beam determines the reactions that can develop. A fixed support provides resistance in both horizontal and vertical directions and also resists rotation through a moment. A pin support provides resistance in two perpendicular directions, but does not resist moment. And a roller support provides only reaction in one direction and allows both movement in the perpendicular direction and rotation. Understanding the support conditions is essential, as they define the unknown reactions that must be determined before analysing the internal forces. We'll begin demonstrating the method with example 1, which considers a simply supported beam subjected to two concentrated loads. The beam is divided into equal segments and the loads are applied at specific locations along the span. From the previous lecture, we've already determined the support reactions which we'll use in our analysis. Our objective is to determine the internal force distributions along the beam. And to do this, we're going to apply the method of sections, derive expressions for the internal forces in each region, and then use them to construct the axial force, shear force, and bending moment diagrams. This example will demonstrate the full procedure before we move on to a more complex loading case. Before proceeding with the internal force analysis, we recall the support reactions for the beam. These were determined in the previous lecture using equilibrium. We'll now use these known reaction values as the starting point for our analysis. This allows us to focus on developing the internal force expressions without repeating the reaction calculations. We now divide the beam into regions using section cuts. The cuts are placed at points to analyse the results in internal forces when loading changes, in this case before and after the applied point loads. This is important because within each region, the loading remains constant, which allows us to write a single set of equilibrium equations. In this example, we define three regions: from A to the first load, from the first load to the second load, and from the second load to the right support. Within each of these regions, we introduce a variable position and derive expressions for the internal forces. By splitting the beam in this way, we ensure that our equations are valid and easy to apply within each segment. Before writing any equations, we set up the structure of our solution. We begin by drawing a clear free body diagram of the beam and leaving sufficient space underneath it for the axial force, shear force, and bending moment diagrams. We also mark the boundaries between regions using dashed vertical lines at the locations of the cuts where the loading changes. This is important because these boundaries define where the equations change from one region to the next. As we analyse each section, we can immediately sketch the corresponding portion of the internal force diagrams in the space below, and this keeps the solution organised and allows us to check consistency between regions as we go. It's particularly valuable in time-bound situations like exams, so by building the diagrams progressively, we avoid having to search back through our calculations at the end and extract values. It also means that even if we don't complete the full solution, we already have part of the diagrams drawn, which clearly demonstrates method and understanding and can gain credit. A clear layout at this stage will make the rest of the analysis much easier and help reduce errors. We now consider the first region from A to B and introduce a cut at an arbitrary distance x1 from support A. This cut is a key step in the method. By cutting the beam, we expose the internal forces that were previously hidden within the structure. At the cut section, we must always introduce three internal actions: axial force, shear force, and bending moment. These must be drawn in their assumed positive directions, consistent with the sign convention we defined. Matching internal forces to balance these out will develop on the other side of the cut. Note that the forces will be equal but opposite in direction, so that when we close the cut, they'll disappear. They are internal forces, right? It's important to remain consistent here. The directions we assume will determine the signs of the results. We isolate the left-hand side of the beam and draw the free body diagram, including the support reaction and the internal forces at the cut. We now solve for the internal forces in the first region. The region is defined between the left support at A and the first applied load at B, and the expressions we derived are valid only within this interval. The total length of this region is 3 meters, so x1 varies from 0 to 3 meters. We start with the free body diagram on the left-hand side of the beam. Cut at a distance x1 from support A. At the cut, we expose three internal actions: axial force, N, shear force, S, and bending moment, M, all drawn in the positive directions according to the sign convention. We now apply equations of equilibrium in the order shown. We'll start with horizontal equilibrium, so the sum of forces in x equals 0, and since there are no horizontal forces, N in this section equals 0. Next, we apply vertical equilibrium, so the sum of forces in y equals 0. We'll just sum up all the vertical forces, so we have minus S plus 100 equals 0, so S works out as 100 kilonewton. So it's a constant throughout this section. And finally, we'll apply moment equilibrium around the cut. We do it around the cut because if we were to do it in any other location, we would have to take into account the internal forces exposed. And just in case we made a mistake with the shear force, we don't want to be dragging it throughout the equations. Plus, we would also have to use the whole equation for the shear force for this. So, doing moments around the cut, sum of moments around the cut equals 0, and we get that the moment, because it's anti-clockwise, so positive, minus 100 times x1 equals 0, and isolating the moment gives us that the moment equals 100 x1. We can now evaluate the bending moment at the boundaries of the region. So at point A, where x1 equals 0, and at point B, when x1 equals 3. So at point 1, we get 0, and at the point when x1 equals 3, we get 3, which gives us 300 kilonewton meters. So from the region from A to B, we can see that the axial force is 0, the shear force is a constant at 100 kilonewtons, and the bending moment varies linearly. These values can now be added directly to the internal force diagrams before we move on to the next region. So let's do that. As we've just seen, the axial force is 0 throughout, so just adding that green line for the axial force. The shear force is a constant, and that just means it's a straight line between A and B at 100 kilonewtons, and the bending moment varies linearly between A, which is 0, and B, which is 300 kilonewton meters. At this point, it's just important to check that the behavior is consistent. Constant shear leads to a linear variation in bending moment, and this completes the first section. We now move on to the second section. This section is defined from A to C, and x2 varies from 0 to 3. So here, x2 is measured from point B. So we've passed 3 meters, and now x2 is from point B onwards to point C. At the cut, we expose the internal forces, drawn according to the sign convention. We'll start with horizontal equilibrium, sum of forces in x. N is still 0 in this section. Vertical equilibrium gives us minus S plus 100, which is the reaction force, and minus 120, which is this force going down. So we get a constant here of minus 20 in this region. Finally, taking moments around the cut, so the sum of moments around the cut is 0. And here we have the moment that we've exposed, so mx2, minus 100, and this time the distance is 3 meters plus x2, and plus 120 times x2, and all that equals 0. So the equation for mx2 equals 300 minus 20x2. We can now evaluate the bending moment at the two boundary points. So when x2 equals 0, we get 300 kilonewton meters, which matches the bending moment that we got at the end of the previous section, which is exactly what we expect, as the bending moment must be continuous when there's no applied moment. At the end of the section, when x2 equals 3, which is point C, we get 240 kilonewton meters. So within this region, the axial force remains 0, the shear force is constant at minus 20 kilonewtons, and the bending moment decreases linearly. This behavior is consistent with what we expect. A constant negative shear force results in a linearly decreasing bending moment. And we can now represent the results for the second section on the internal force diagrams. So starting with the axial force, this remains 0 in this section. And for the shear force, we get minus 20 kilonewtons. That means that immediately after point B, the shear force drops from 100 kilonewtons to minus 20 kilonewtons due to the applied 120 kilonewton load. Between B and C, the shear force remains constant at minus 20 kilonewtons. So the shear force diagram is just a horizontal line in this region. And now looking at the bending moment at B, x2 is 0, we got 300, which matches what we got before. Excellent. And then we vary linearly to the second point we calculated, where the moment was 240 kilonewton meters. And we can now move on to the third and final section. This section is defined as A to D, and the variable x3 varies from 0 to 3 meters. Here, x3 is measured from point C, which is the start of the region. We take a cut at a distance x3 from C and isolate the left-hand side of the beam. After exposing the internal forces, we can now apply equilibrium to find the internal forces. Once again, starting with the sum of forces in X, we find that the axial force is 0 in this region as well. Looking at vertical equilibrium, we have minus S plus 100, minus 120, and now also minus 60. All that has to equal 0. So the shear force in this section works out as minus 80 kilonewtons. And finally, we take moments around the cut. In this case, we have a positive moment, mx3, and then we have a negative moment from the reaction force of 100. This time, the lever arm to the cut is 6 meters plus x3. We also have a positive moment from the 120 point load. Its distance is 3 plus x3. And we also now have the force of 60, which is multiplied by the distance x3. Rearranging, we get that mx3 equals 240 minus 80x3. Once again, we can evaluate the bending moment at the two boundary points. At the start of the section, when x3 equals 0, that corresponds to point C, and we get 240 kilonewton meters. This matches the value that we obtained previously, which confirms continuity. At the end of the section, when x3 equals 3, we get 0, and this is exactly what we expect at a simply supported end, where the bending moment must be 0. These two conditions provide us an important check to ensure that the analysis is correct. And we can now represent the results for the final section on the force diagrams. Axial force remains 0. For shear force, we observe that the values change in steps along the beams. So at point C, we can see that we've got a further drop of 60 kilonewtons. So in the final region, the shear force is constant at minus 80 kilonewtons. And at point D, the reaction of 80 kilonewtons brings the shear force back to 0. Looking at the bending moment diagram, we can see that at point C, it's continuous with what we calculated previously, and it drops down linearly to 0, which is exactly what we expect at an end support. We can also note that the maximum and minimum bending moments occur when the shear forces cross 0. In this example, the shear force changes signs at point B, and this corresponds to the location of the maximum bending moment. So overall, we see clear relationships between the load, shear, and bending moment. Point loads create jumps in shear, constant shear produces linear bending moment, and the extreme moments, so the max or min moments in bending, occur when the shear is 0. So now, just to demonstrate a point, let's repeat the analysis of the third section, but this time let's start from the right-hand side. This section is defined from point D to C, and the variable x3 in this case varies from 0 at point D to 3 meters at point C. So once again, the expressions derived in this region will only be valid within this region from D to C. At the cut, we expose the three internal forces: axial force, shear force, and bending moment. Now, it's very important that all of these are drawn according to the sign convention. So I've included this just to show that we can analyze a section from either direction, provided we remain consistent with the sign convention. And I've just left a snippet of the sign convention that we carried from the left side just to show you that all the values should be equal but in opposite direction to the ones we're exposing now. Now, in this case, as we can see immediately, that working from the right-hand side is simpler, and that can happen in a lot of beams just depending on the loading and support arrangements. It's also a useful check if we start from this side, because the results obtained from the right-hand side should meet the results obtained from the left-hand side at the same boundary points. So let's quickly do this. Sum of forces in X, we still get that the axial force is 0, as we expected from what we already analysed. Looking at vertical equilibrium, here if we sum all the forces in the vertical direction, we have S plus 80 equals 0, so S works out as minus 80 kilonewtons. So the shear force in the section is constant and equal to minus 80 kilonewtons, which exactly matches the value obtained previously when we analysed this same section, but from the left-hand side. And finally, the moments around the cut, we get that minus the moment, because this time the moment is clockwise, plus 80x3 equals 0, so the moment is 80x3. If we put in the two boundary conditions, so when x3 equals 0, so at point D, we get 0, just as we got in the previous calculations, which is exactly what we would expect at a simply supported end where the bending moment must be 0. And at the other end of the section, when x3 equals 3, that corresponds to point C, and the moment there is 240 kilonewton meters. And that matches the bending moment that we obtained previously at point C, when the same section was analysed from the left-hand side. So this is exactly what we expect. Both approaches should meet at the same boundary value. This confirms we can analyse the beam from either side. As long as we apply the sign convention consistently, we'll get the same internal force results. It also shows that working from the right-hand side can sometimes be more convenient and provides a good check that the two parts of the solution meet correctly. Let's just make sure that we completely understand how to draw the bending moment diagram correctly and identify the tension side using the diagram on the right. A key rule is that we draw the bending moment on the tension side of the beam. To determine which side is in tension, we look at the direction of the bending moment at the cut, as shown in the diagrams. The assumed direction of the moment tells us how the beam is trying to deform locally. If the moment causes the beam to bend so the top fibers are pushed together, then the top is in compression. At the same time, the bottom fibers are being pulled apart, which means the bottom is in tension. And this corresponds to what we call a positive bending moment, or sagging behavior. In this case, the bottom side is the tension side, and this is where we draw the bending moment diagram. Drawing on the tension side is important because the bending moment diagram then mirrors how the beam actually deforms under load. And by drawing it on the tension side, the diagram reflects the physical shape of the beam rather than just showing numerical values. So for example, in reinforced concrete. Concrete is very strong in compression but weak in tension. So we add reinforcement bars where the tension side is, because that's where cracking occurs and that's where we need the reinforcement. So by drawing the bending moment diagram on the tension side, we can immediately identify the critical regions of the beam and see where reinforcement needs to be placed. So this approach of drawing on the tension side links the analysis directly to both the physical behavior of the structure and the practicality in design. We can now summarize the internal force diagrams for the beam. The shear force diagram changes in steps at the locations of the point loads. Starting from A, the shear force is 100 kilonewtons, drops by 120 to minus 20 kilonewtons, and then drops again by 60 at point C to minus 80. At support D, the reaction brings the shear force back to 0. The bending moment diagram is drawn on the tension side, as we just discussed, and varies linearly within each region, reflecting the constant shear force. It increases from 0 at A to a maximum of 300 kilonewton meters at B, then decreases to 240 kilonewton meters at C, and finally returns to 0 at D. The maximum bending moment occurs where the shear force changes sign, which is in this case at point B. Overall, point loads cause jumps in shear, constant shear produces linear bending moment, and the diagrams reflect the physical behavior of the beam. We now consider example 2. This is a simply supported beam subjected to both a point load and a uniformly distributed load. In addition, the point load is inclined, which means it must be first resolved into horizontal and vertical components before the analysis. This will introduce a horizontal force, so it will introduce an axial force into the problem, unlike the previous example where the axial force was 0 throughout. So in this example, we'll extend the same systematic approach, but now include the effect of both distributed loading and axial force. We begin by resolving the inclined 240 kilonewton load into its components. The approach to calculating support reactions has been covered in the previous lectures, so here we'll just focus on the key steps and results. The vertical component of the load is 120 kilonewtons and the horizontal component is 207.8. These components are then applied to the beam. From equilibrium, we can obtain the support reactions, and at support A, we have a vertical reaction of 100 kilonewtons and a horizontal reaction of 207.8 kilonewtons. At support E, we have a vertical reaction of 80 kilonewtons. These reaction values will now be used as the starting point for determining the internal forces in each section. We now divide the beam into regions using section cuts. The cuts are placed at points before and after loading changes. In this example, this occurs before and after the point load and at the uniformly distributed load. This results in 4 regions. Within each region, the loading is consistent, allowing us to write valid equilibrium equations. We will analyse each section separately, deriving the expressions for axial force, shear force, and bending moment. Once again, before writing the equations, we'll set up the structure of our solution. We'll draw the free body diagram and leave space below for the axial force, shear force, and bending moment diagrams. We'll once again mark the boundaries between regions using dashed lines, which correspond to the boundaries of the section cuts. As we analyse each section, we will progressively build the internal force diagrams. We now analyse the first section from A to B, with x1 varying between 0 and 3 meters. The process is the same as in example 1, but we now have a reaction from the component of the inclined load. So, starting with applying horizontal equilibrium, sum of forces in x equals 0, this time we have N1, which is the axial force, plus 207.8, which is the reaction. And that gives us an axial force of minus 207.8 kilonewtons. It tells us that the axial force in this region is constant and compressive. From vertical equilibrium, the shear force works out as 100 kilonewtons and is consistent throughout the region. And from doing moment equilibrium around the cut, we get that the moment mx1 equals 100 x1. Applying the two boundary conditions, when x1 equals 0, we get 0 as expected, and when x1 equals 3, we get 300 kilonewton meters. We can now represent the results from the first section on the internal force diagram. Starting with the axial force, we have a constant value of minus 207.8 kilonewtons, and this indicates compression, and it arises from the horizontal component of the inclined load. For the shear force, the value is 100 kilonewtons, so the shear force diagram is constant between A and B. And for the bending moment, we have a linear variation from 0A to 300 kilonewton meters at B. We can now analyse the second cut from A to C, with x2 starting at B and varying from 0 to 2 meters. So once again, 3 equations of equilibrium starting with our horizontal forces. Here we have that nx2 plus 207.8 from the reaction force minus 207.8 from the inclined load equals 0, which leads to the axial force being 0. From vertical equilibrium, the shear force now becomes minus 20 kilonewtons, and looking at the bending moment at the cut, we get 300 minus 20x2, which means that our bending moment will vary linearly, right, because it's just a function of x. Evaluating at the boundaries gives us 300 kilonewton meters at B, as expected because the moment is continuous, and 260 kilonewton meters at C. And we can now add these results to the diagrams. So the axial force reduces to 0 at point B and remains 0 throughout this region. The shear force drops from 100 to minus 20 kilonewtons at B due to the applied load and remains constant until C. And the bending moment continues linearly from 300 kilonewton meters at B to 260 kilonewton meters at C. So in this section, the main change is the disappearance of the axial force, while shear and bending moment follow the same behavior as in example 1. Let's move on to the third section. This section is defined from A to D, with x3 measured from point C and being between 0 and 2 meters. So x3 equals 0 corresponds to point C, and x3 equals 2 corresponds to point D. The expressions we derive will only be valid within this interval. This section includes a uniformly distributed load, which changes the behavior of the internal forces. Let's apply equilibrium to determine how the axial force, shear force, and bending moment vary. So starting off with a sum of forces in x, which gives us the axial force, we can see here that really nothing has changed. We've added 207.8, taken away 207.8 once we passed the inclined load, so we end up with an axial force in this region of 0. Looking at the vertical forces, we've got minus S, which is the shear force, plus 100 from the reaction force, minus 120 from the point load, and now we have minus 30 times x3. So if we recall, a force of a UDL is always the area that we pass. So the height of the rectangle of the UDL is 30, and the distance in x is x3. So the force will change depending how far along the UDL we are. So generally here, our equation for shear is going to be minus 20 minus 30 x3. If we put in our boundary conditions, so what happens when x3 equals 0 and what happens when x3 equals 2, we get minus 20, which matches our previous value for shear, and we get at the end minus 80. So in this case here, we can see that under the UDL, the shear force varies linearly. Looking at the bending moment, we'll sum the moments around the cut. So here we've got mx3, the moment, minus 100, so that's the reaction force, this time times a distance of 5 meters, that's until point C, plus x3, plus 120, that's the first point load, times 2 plus x3, and now we have the UDL. So the force of the UDL is 30 times x3, that gives us the force, and the distance from the centroid of that UDL, which is just a rectangle because it's a UDL, to the cut is always going to be x3 divided by 2. And all of that needs to equal 0. So here we have a parabolic equation of 260 minus 20x3 minus 15x3 squared. So you can already see that the moment is going to vary in a parabolic way. And if we put in the two boundaries, so what happens when x3 equals 0, we get 260 kilonewton meters. That's a good sign, that matches what we had before. And when x3 equals 2, so when we're at point D, we get 160 kilonewton meters. We can now represent the results for this section on the internal force diagrams. First, we'll check the values at the start of the section. So as we saw before, the shear starts at minus 20 kilonewtons and the bending moment starts at 260 kilonewton meters. And these match the values that we obtained at the end of the previous section. Unlike in previous sections, the shear force is no longer constant. It decreases linearly from minus 20 kilonewtons at C to minus 80 kilonewtons at D. The linear variation is due to the uniformly distributed load acting on this region. The load is applied continuously, so the shear force changes continuously along the beam. Looking at the bending moment diagram, instead of a straight line, we now have a curve. It goes from 260 kilonewton meters at C to 160 kilonewton meters at D, following a parabolic shape. And this occurs because the bending moment is obtained by integrating the shear force. And since the shear force varies linearly, the bending moment must vary quadratically. So this section highlights an important relationship between loading and internal forces. A uniformly distributed load produces a linear variation in shear and a parabolic variation in bending moment. And this is a key concept that we will use repeatedly in beam analysis and design. We can now analyse the final section. We'll take it from E to D, so we'll use the right-hand side cut, just because it's going to be much simpler. In this case, X4 starts from the support and is therefore measured from point E. At this cut, we once again introduce the internal forces and apply equations of equilibrium. So, sum of forces in X gives us that the axial force is 0. From vertical equilibrium, we obtain that the shear force is minus 80. And taking moments around the cut gives us that the moment mx4 equals 80 times x4. Evaluating the results at the boundaries, when x4 equals 0, which is point E, the bending moment is 0, which is exactly what we expect at a simply supported beam. And when x4 equals 2, which corresponds to point D, the bending moment is 160 kilonewton meters, which matches the value obtained previously. This confirms that the solution is consistent and that analysing from either side gives us the same internal force results. And we can now complete the internal force diagrams for example 2. Starting with the axial force, we see that it's constant and compressive between A and B due to the horizontal component of the inclined load. After point B, the axial force reduces to 0 and remains 0 for the rest of the beam. For the shear force, we again observe step changes at the point loads. At point B, the shear drops from 100 kilonewtons to minus 20 kilonewtons, and in the region with the uniformly distributed load, the shear force varies linearly, decreasing from minus 20 kilonewtons at C to minus 80 kilonewtons at D. At support E, the reaction brings the shear force back to 0, completing the diagram. Looking at the bending moment diagram, we see linear variation in the regions with no distributed load and a curved parabolic shape in the region where the UDL is applied. The bending moment increases to a maximum of 300 kilonewton meters at B, where the shear force passes through zero, and decreases to 260 kilonewton meters at C, and a further 260 kilonewton meters at D. Finally, it returns to zero at support E, as expected for a simply supported beam. Throughout the beam, the diagrams are continuous and consistent between sections, and the values match at the boundaries. So this example brings together all key behaviors: axial force from horizontal loading, step changes in shear from point loads, linear variation in shear from distributed loads, parabolic variation in bending moment due to the UDL. These relationships are fundamental to understanding beam behavior and will be used repeatedly, as I said, in analysis and design. Thank you for joining me. I hope that this systematic approach has really clarified how to approach beam analysis. The more you practice and the more careful you are at applying this system, the easier it'll get, and also the more evident the relationships between shear and moments, for example, will become. Using this approach, you can solve whatever beam under whatever loading as long as you're consistent. The main thing here is practice. I have quite a lot of solved examples, so head over to those and keep on practicing.